Okay, this is the tutorial on superposition and reflection of pulses for Physics 106. And I apologize for my voice. I have been sick the last couple of days with a bad cold, and it is what it is. So I'll uh, try to make my best of it. I'm going to share my screen. Okay. So what you're seeing now is what you should have on the table next to you. This is the tutorial handout that you bought over at the bookstore, that little packet that costs $5.75. And that's what we're going to be going through is the 4 pages of that tutorial. So let me just walk us through it. Pulses on a spring. If we were doing this in person, each group of four individuals would have a really long spring, and you could uh, play with making different pulses on it. These tutorial handouts were written at University of Washington, where they only had a short amount of time to get through the tutorial, 50 minutes. And so instead of letting students play with the springs, tutorial instructor demonstrated the pulses. Now, we're in a situation where we don't even have springs. I've got a big box of them, but we're not doing in-person tutorials. So what we're going to do instead is just splice in a video of two of my friends, Tom Woods and Paul Ruckheimer, creating pulses uh, on a long spring with for this part of the tutorial. So uh, it says a piece of yarn has been attached to the spring. How did the motion of the yarn compare to the motion of the pulse for each type of pulse that you observed? Well, the two pulses that you were supposed to observe are a longitudinal pulse and a transverse pulse. Well, the longitudinal pulse we demonstrated in lecture. That was the demo with the slinky that was hanging from wires. And in that case, we created a pulse. And let me put a little piece of yarn there. Okay. And we created a pulse by, oh no, sorry about that. We created a pulse by uh, pulling part of the spring back, and what we found was that this uh, piece of yarn moved back and forth parallel to the motion of the pulse. So the pulse moved from left to right. And the little piece of the spring that's carrying the pulse moved parallel to the direction that the pulse was traveling. A transverse pulse, on the other hand, uh, we found that if we moved part of the spring like that, that a pulse would travel down the spring. And again, if we put a little piece of yarn on there, as the pulse went by, the yarn would move up and then back down. And so transverse means perpendicular, and longitudinal is parallel. Okay. The terms transverse and longitudinal are often used to describe the types of pulses that you have observed in the demonstration. To what feature of the pulse do these terms refer? And that's going to be the displacement of the spring from equilibrium. For the rest of this tutorial, we're going to focus on transverse pulses along the spring. And that's because with the longitudinal pulses, it's really hard to visualize or even see the amplitude, whereas it's very, very apparent what the amplitude is with a transverse pulse. During the demonstration, did any of the following features change significantly as a pulse moved along the spring? Uh, and we want to ignore what happens when it reaches the end of the spring. We're going to talk about that on page 4. The key word in this sentence is significantly, significantly. Um, well, let's go and watch that video of the transverse pulses now.
Okay. Okay, so we're investigating what effect the width of a pulse on this spring is going to have on the speed of the pulse. So I'm going to send the pulse down. Going to come back. Now, so that width is the width of the area between my feet here. So now I'm going to increase the width, and we'll see if that has an effect on the speed. What do you think, Dr. Ruckheimer? Does that have any effect?
Doesn't look like
Doesn't
it.
look like it. Okay, so let's try amplitude. What would increasing the amplitude of the pulse do to the speed of it traveling down to Dr. Ruckheimer and back? Down and back. Now I'm going to increase that amplitude. Doesn't seem to have any effect at all. So now we're going to increase the tension in the spring and see if that has any effect on the speed. Seems like that does. A lot faster now. Makes sense. Okay.
Okay, what you should have seen was that as the pulse went down the spring, um, the amplitude of the pulse did not change significantly. I mean, due to friction, we lose a little bit of the energy and it might get a little bit smaller. If we had greased down that floor, it wouldn't have gotten smaller. The width of the pulse doesn't change. The shape of the pulse doesn't change significantly, and the speed does not change significantly. So that's just one pass of the pulse from one side of the spring to the other side of the spring. Well, now we want to talk about what changes could we make to our setup that would change the speed of a pulse. And from one pass to another pass. And the we're going to go in reverse order. The shape of the pulse, uh, what you I hope saw was that the shape did not uh, affect significantly the speed of the pulse, and the width did not, and the amplitude did not. But the tension, by stretching the spring to a greater length, that was a big ol' yes. That sped up the pulse significantly. And what I presented in lecture, without really showing you the math that justifies it, was that for a pulse on a spring or a string, the speed of the pulse is given by the square root of the tension in the spring divided by the mass density where that mass, it's often called the linear mass density, is the mass of the spring divided by the length of the spring. Okay. And you remember that with simple harmonic motion, the two things that were important were the restoring force and the inertia, how hard it is to get things to speed up or slow down. And the tension is the restoring force. That's the pull on each piece of the spring by its neighbors to get it back to equilibrium. And the mass per unit length, the linear mass density, that's the inertia. That's how hard it is to speed up or slow down. Now, um, I'm going to go to page two. Um, Page two is showing a set of pictures that look fairly primitive, and they are. Um, these pictures came from a very famous introductory physics textbook that was created by a committee in the 1960s, PSSC physics, and this is what Lillian McDermott was comfortable with. This is what she was familiar with, and it teaches the principle, even if it's not the highest tech photography. But what we have here are some snapshots that show two pulses approaching each other on a spring. The pictures were taken at equal time intervals, so it's a kind of a strobe picture. The pulses are on the same side of the spring. In other words, each of those pulses displaces the spring towards the top of the page. And the first thing we want to discuss here is what happens when these two pulses meet. The one is going to the right, and this one is going to the right, and this one's going to the left. And oh, I didn't do that very well, did I? Okay, there we go. And when they meet, do they pass right through each other, or do they bounce off of each other like rubber balls and go back the way they came? And what I hope you see in these pictures, I mean, if this was the picture at noon, and this is noon plus 1 second, and this is noon plus 2 seconds, and noon plus 3 seconds, and you get the idea. I hope what you see here is that they pass through each other. And the evidence for that can be found in picture two and picture eight. If we look at picture two, um, the the narrow pulse is on the right and the wide pulse is on the left. And then if we go down at picture eight, we see the narrow pulse is on the left and the uh, wide pulse is on the right. So these have just passed right through each other like ships in the night, just going on their way. Now, when the pulses completely overlap, as shown in figure five, um, how does the shape of the disturbance in the spring compare to the shape of the individual pulses? Well, it's larger. Indeed, we can show that it is the sum of the pulses. We just add them up. Okay, we just take the two displacements and add them together. Describe how you could use the principle of superposition to determine the shape of the spring at any instant while the pulses overlap. And that would be that pulse 1 plus pulse 2 is equal to the total displacement of the spring. And that's what superposition means. It just means add them up. It's just a fancy word for add them up. Okay. Now, in, whoa, what did I do now? Okay. Let's get rid of that. Okay. Sorry about that. I'm getting used to this new technology. In this exercise at the bottom of the page, two pulses, 1 and 2, are approaching each other as shown. And the bottom diagram shows the location of pulse 1 a short time later. Now, I hope you can see that pulse 1 did not change its shape or its amplitude, just its position along the spring. And if we look at the leading edge, the front of the pulse, it moved 1, 2, 3, 4, 5 squares to the right. Okay. And of course, the trailing edge moved 1, 2, 3, 4, 5 squares to the right. So the first thing we're asked to do is to um, figure out where pulse 2 is going to be at this time. Let's say this was at noon and this was at noon plus 5 seconds. Okay. Well, um, I know that these two pulses are on the same spring, and that means they have the same mass density. And it also means that they have the same tension. And since the speed is, whoa, that didn't work. Since the speed is equal to the square root of the tension over the mass density, uh, they've got the same speed. And so that means that this pulse here is going to move 5 squares to the left. And so if it started out here, and I go 1, 2, 3, 4, 5, that means that it's going to go up in 2, and down in 4. 1, 2, 3, 4. Okay, something like that. And again, I'm not always the best drawer, but I'll try my best. Actually, this technology has a, okay, that's better. Now, what we're going to do is we're going to add up those two pulses. Right here, I've got 0 and 0. And here I've got 0, 0.5. And here I've got 0 and 1. And here I've got 1 and 1.5. And that's going to be 2.5. And here I have 2 and 2, and that's going to be 4. And here I have 1 and 1.5, that's going to be 2.5. And here I have 1 and 0. And here I have a half and 0. And there I've got 0 and 0. So the spring is going to look like the tail end of 1, and then they're going to overlap like this, And then it's going to look like the tail of two. Okay. And again, I wish I were better at drawing, but I hope you see the process that we're doing. Um, at each point, I took what the dashed line that was pulse one, what displacement it had, and I added it to the displacement of the red line that was pulse two. And so, for example, right here, I had two squares up from the dash line and two squares up from the red line, and that gave me a total of four at this point here. Okay, moving right along here. Um, Again, we're going to deal with some pictures from that PSSC textbook, but this time we have pulses that are coming in from both sides, left and right, but this time they're not starting on the same side of the spring. One's on top and one's on bottom, but they have a certain symmetry that I imagine took them a while to set up. Um, if we look carefully, we see that each of these pulses have the same width and the same amplitude. And they start out um, equidistant from that point Q. In other words, we chose point Q to be halfway between where they started out. And then we're told that these snapshots were taken at equal time intervals. Again, it's a strobe photograph. Is the behavior of the spring consistent with the principle of superposition? If so, which quantity is added in this case? Well, it definitely is. We see in picture five, we see that these two pulses, when they add together, one's on top, one's on the bottom, and so essentially they cancel each other out. And so the thing that's added is again, the displacement from equilibrium. Okay. And um, below is a simplified representation of both individual pulses at a time between instants shown in snapshot 4 and 5. Skep Sketch the shape of the spring at the instant shown. Now, you'll notice that these pulses that are shown here um, are idealized. That means I've got straight lines and I've got a kink right here where it uh, changes direction very quickly. You're never going to see pulses like that in nature. And we explore that in the tutorial homework, uh, the homework that's associated with this particular worksheet. But these are easy to work with mathematically. And so we're going to pretend that these pulses were nice and clean like that. Now, to find the shape, um, I use superposition again. I go along and I say, well, uh, here I'm adding 0 and 0. Here I'm adding 1 and 0. And here I'm adding 2 and 0. And here I'm adding 3 and negative 1. That's 3, and that's negative 1. And so that's going to give me 2. Put it right on the crosshair there. And then here I've got 2 and negative 2, and that's going to be 0. And then here I've got 1 and negative 3, that's going to be negative 2. And here I've got 0 and -2. And then I've got -1 and 0 and 0 and 0. And so what this is going to give me is it's going to go up like that. It's going to go over like that. It's going to go down like that. These are straight lines. I'm sure you can't tell. Over like that and up like that. Okay. So this would be flat here, flat there. Okay. This would be okay. Let point Q be the point on the spring midway between the pulses as shown. Describe the motion of point Q during the time interval shown. Well, if you take a piece of paper and place that piece of paper uh, along the equilibrium position, uh, what you find is that point Q doesn't move. And the reason it doesn't move, I hope you see, is due to the symmetry. And that's because these two pulses are coming at the same speed. And so the same part of the pulse arrives uh, at point Q at the same time. In other words, when the peak of this pulse on the left gets to point Q, the negative peak of this pulse also gets to point Q and they cancel. When a point that's halfway up this pulse on the left gets to point Q, it meets a point that's halfway down on this negative pulse on the right. And so there's always going to be the same displacement from the left pulse up as there is from the right pulse down, and it's always going to add up to 0. Now, which, if any, of the following changes would affect the motion of point Q? Well, if I double the amplitude of both pulses, I don't change the symmetry. It's still going to be two pulses that are the same size, one on top and one on the bottom. So this would not affect. And doubling the amplitude of just one pulse or doubling the width of just one pulse, that is going to cause point Q to move because I have broken the symmetry. I have broken the symmetry. So now they're asking us to consider this asymmetric pulse. Again, it's got this idealized kink in it that nature doesn't really allow. What shape would a second pulse need to have in order that point Q not move as the two pulses pass each other uh, as they go through each other? And we want to indicate that shape, the location, and the direction of motion of the second pulse. Well, it's point Q has to be in the center, and then when this peak here reaches point Q, I want a negative peak there. So this went up 2 in 2, and so this is going to go down 2 in 2, and then this pulse goes down in four squares. So this is going to go up in four squares. That's one, two, three, four. And this one's going to be going that way. And so you see that, let's see if I can make that cleaner. Okay. So now when this point is at point Q, so will this point due to symmetry, and they will cancel each other. So what you see is that the original pulse, the pulse that's going to cancel it is going to be reflected across point Q and then inverted. So if I could do that with my hands, it's, let's see, it's going to be reflected across point Q and then inverted. Ah, that might not speak to your soul. I'm doing my best here. Okay, now we're going to talk about reflection. What happens when a pulse traveling down a spring hits a boundary? And in this case, we're going to make the boundary a wall where we tie one end of the spring to a wall so that where it's tied to the wall, it can't move. It's forced to be right there. Now, in the homework associated with this tutorial, we'll look at a different boundary, a boundary where the spring is free to move without any friction along the boundary. But we'll save that for later. For now, we're looking at a fixed end where it's tied to a wall. And what we find, again, from these snapshots from the PSSC textbook, is a pulse on top uh, comes towards the boundary, towards the wall, and when it meets the wall, um, it disappears. And then, lo and behold, a pulse emerges from the wall, but now it's flipped upside down. It's on the bottom, and it's moving to the left. So, uh, so let's be clear about what's happening here. A pulse on top comes in, disappears, and comes back, reflects back on the bottom, on the opposite side. Okay. Now, in the process of hitting the wall, the the shape of the pulse gets all changed in a complicated way. Now, one way to explain this is with mathematics, and it turns out that the name of the game in physics is to describe the real world behavior that you're seeing with a mathematical equation. We call it an ordinary differential equation. And then the solution to that equation tells us what that pulse is going to look like at each stage of the collision when it hits the wall. And that's a kind of a complicated uh, mathematics. The classes in ordinary differential equations aren't taught at the um, freshman or sophomore level. Those are higher level classes. Um, but it turns out we don't need to use that mathematics to understand what's going on in this reflection from the boundary, because we can build a model that gives us the answer without all of the fancy mathematics. What we see is a pulse coming in on the top and coming out on the bottom. And in the process, the point where it's tied to the wall never, ever moves. Okay. So, um, let's go through these questions. Describe the similarities and differences between the incident pulse, the pulse moving towards the fixed end, and the reflected pulse. Well, the similarities are they have uh, same width, same amplitude, uh, and same speed. What's different is uh, going from top to bottom. The incident pulse, the original pulse, was on the top, and the reflected pulse is on the bottom. Now, they're asking us to uh, go back to page 3 and to take a piece of paper, and you're going to have to do this because my technology is not going to let me do this. But if you were to um, maybe let's see what I can do. If you were to cover up the right side with a piece of paper and just look at the left side, what you see is a pulse coming in on the top and it approaches the wall and then it meets the wall and then it starts to disappear and then it completely disappears. And then lo and behold, a reflected pulse comes back the other way on the bottom and moves away from uh, the wall. Okay, so essentially, um, point Q in this situation doesn't move because there's that symmetric pulse coming through on the bottom that cancels everything out. But whether point Q doesn't move because of that symmetry or because it's tied to the wall doesn't matter. It doesn't move. In both cases, I've got a pulse coming in on the top, coming away on the bottom, and point Q doesn't move. And so this gives us a mechanism of solving this reflection at a boundary without doing the fancy mathematics. And that's what we want. We want to avoid the fancy mathematics. And so let's go back to that last page. Um, how does the behavior of the uncovered portion of the spring, including point Q, compare to the behavior of the spring shown at right? Exactly the same. Okay. Okay. The results of the exercise above suggest a model for the reflection of pulses from fixed ends of springs. We imagine that the spring extends past the fixed end and that we can send a pulse along the imaginary portion towards the fixed end. We choose the shape, orientation, and location of the imagined pulse so that it passes the incident pulse, that as it passes the incident pulse, the end of the spring remains fixed. Let me say this in different words. The spring is connected to the wall. With your mind, with your imagination, you pretend the wall's not there and that the spring extends back behind the wall in the darkness where the spiders live. And you pretend that there's a pulse back there with the spiders that's coming towards you as the original pulse is going away from you. Okay. And these two pulses meet at that wall, okay, where the spring is tied down. That's the point Q. And so that imaginary pulse that's coming from behind the wall has to have that same symmetry that we found on page 3 of this tutorial. Has to have the same width, the same amplitude, but it's inverted. One's on top and one's on the bottom. Okay. Now, um, we can use this idea to predict what the pulse is going to look like as it collapses, as it goes through the process of hitting this wall that it's tied to. What I have here is an idealized pulse. It goes up in 2 squares and down in 4 squares, and it's traveling at a speed of 1 meter per second. And we're told that 1 square on this grid is 10 centimeters. What that means is that for every, it travels 1 square to the right for each tenth of a second. Okay. So in 2 tenths of a second, we want to figure out what this is going to look like in 2 tenths of a second and 4 tenths of a second and 6 tenths of a tenths of a second. So the leading edge of this pulse is 1 square from the boundary. So in 2 tenths of a second, it's going to be 1 square beyond the boundary. And then it's going to go up in two and down in one, two, three, four. Okay. So that's where it's going to be. And if I, let's try green. Now, the pulse over here is going to start like that, and it's going to the left. So just like this pulse is going to be 1 square beyond the boundary, so is the imaginary pulse. Okay, and it's going that way. Now, if I let's use blue for the total. Um, Here, up until here, I've just got the red pulse. And then I have here I've got +1 and let's see. I've got to fix this picture here. Okay. Ah, this is supposed to start here, go through that +1 point to there. Okay. Now, let's go back to blue. Here I've got a +1 and here I've got a -1, and that's going to give me 0. And so you see that at 2 tenths of a second, it pretty much looks like the original pulse, but the front end's been kind of crumpled a little bit. Now, let's look at 4 tenths of a second. And now the leading edge is going to be 3 behind. And so it's going to go up like that and down 1, 2, 3, like that. Okay. And it's moving to the right. The green pulse is going to be out here, three squares to the left, and like that. And it's going to the left. Okay. And now with our blue, we're going to add them up. Well, let's start back here at the wall. Right here, I've got 1.5 and -1.5. That's going to be 0. And here I have 1 and -2, and that's going to be -1. And here I have 1/2 and -1, and that's going to be -1/2. And here I've got 0 and 0. And so what you see is that the reflected pulse is just starting to emerge and go to the left there. And now at 6 uh, tenths of a second, if I go back to the red, uh, only the very 1, 2, 3, 4, only the very tail of the original pulse is still in front of the wall. And if I look at the green, only the very tail of the green, 1, 2, 3, is behind the wall. And so now if I add them up, superposition with the blue, you see that it's mostly the reflected pulse. But right here, I've got a half from the red and a -1/2 from the green, and that gives me 0. So you see that at 2 tenths of a second, it's just the front of the pulse that's crumpled. At 6 tenths of a second, it's just the tail end of the pulse that is crumpled. And this would be traveling away from the wall. Okay. Now, you're supposed to be shown a demonstration of what happens when a pulse meets a free end. And I'm going to splice in a video right here again from my two friends, uh, Tom Woods and Paul Ruckheimer, that will demonstrate that. And that will get you ready to solve your tutorial homework that's associated with this tutorial. Thank you for your patience with my scratchy voice and with this new technology. I'm going to now end this video. Goodbye.
Yep. Okay, so I'm going to send a pulse down this spring with an amplitude of about, oh gosh, it should miss the cups going down. And let's see what happens to the cups when the pulse hits that big stem and returns. Again. Okay, now we're going to do a free end reflection. And this is going to keep an eye on what happens to the large white styrofoam cups. That's different. Okay.